and welcome to the fourth video under coordination compounds. Today's topic is isomerism. Isomerism means the compounds that have the same molecular formula but different molecular structures. The major classifications of isomerism are structural isomers and stereoisomers. Let us look into structural isomers first. Structural isomers are of five types: ionization, hydrate, linkage, coordination, and ligand. Ionization isomers. These are the compounds which have the same molecular formula but different ion. For example, let me write down a compound. If there's a compound, let's say CO. So now you can see two examples, that is CONH3 5BrSO4 and CONH3 5SO4Br. They are the same in the molecular formula, but the ion inside the brackets is different. So basically what happens is when these are reacted, uh, like uh, when the Br is inside the bracket, it's red violet, and when it's reacted with BaCl2, it gives a precipitate because SO4 reacts with BaCl2, but Br doesn't, right? Because Br is inside the brackets. Similarly, in the second example, where Br is outside but SO4 is inside, it is red in color and gives a precipitate with AgNO3. When AgNO3 is reacted with this compound, it gives a precipitate with Br. That means it gives AgBr. Now moving on to hydrate isomerisms. In hydrate isomerisms, there's a difference in the water molecules. Like again, let me write down an example. Yeah, so I've written down an example, that's CrCl3.6H2. Now this can be written into three forms. The first structure can be CrH2O6 Cl3, whereas the Cl3 is outside the bracket. Then we come to CrH2O5 Cl, one Cl inside, since Cr has to bond with 6 of the ligands in total, and then 2 of the Cl2 outside, and then one H2 outside. Now in the third way we can write CrH2O4 Cl2, one Cl outside, and 2 H2O outside. Now these all will have different properties because they have different structural formulas, right? So this would be violet, this would be blue, and this would form dark green in color. Now moving on to linkage isomers. Linkage isomers are basically where you have the donor groups like the nitro or the nitrito group. The nitro is the NO2 and the nitrito is ONO, where you can see that NO2 and ONO can also be two oxygen plus one nitrogen, but they are different, right? They are basically ambidonor ligands where you have two donors, where O is also a donor and N is also a donor. That's where it's called the linkage isomers. Like we can have CONH3 5ONO2 minus or NO2 2 plus, right? Then we have coordination. In coordination, both cation and anion are present in the isomers, right? Like CrNH3 6 3 plus and CrSCN6 3 minus. Here both have the same formula, but again one has the cation and one has the anion. Moving on to the last classification for structural isomers, that is ligand isomers. Here, for example, I would give you COCl2, AN2Cl, and then we have CaCl2, TN2Cl. Here you can see that the ligand that is present is different, but the rest of the whole formula is the same. So that's how you can identify the ligand isomers, right? Moving on to the stereoisomers. Stereoisomers are basically classified into two types, that are geometrical and optical. Geometrical isomers are also called as cis and trans isomers because here you can see the structure is different when you draw it. Like for example, like here I've written an example of PtCl2NH3 twice, right? So here you can see that when the same ligand is on the same side, that is we have Cl and Cl on the same side, and then NH3 and NH3 on the same side, then it is called cis isomer, right? And similarly, when in the same formula but the ligand are on opposite sides, that is NH3 and NH3 and Cl and Cl are on opposite sides, it's called trans isomers. Hence, its geometrical isomers are also called cis and trans isomers. Okay, now here I have written an example for optical isomers. So what are optical isomers? Basically, when the compound is, moved to a polarized, plane polarized light, the image that is formed is non-superimposable mirror image, and they do not possess plane of symmetry. So what this means is when you pass the compound through plane polarized light, it is turned to 180 degrees. And if you put these two images on top of each other, they do not fit in symmetry, which means they are not superimposable, right? So here's an example that I've said. Like you can see, this is the plane polarized light that we move it to, and then it just becomes opposite. So when you place this on top of this, they do not impose, right? So they are non-superimposable, and that's how you identify optical isomers. That is it for this video. In the next video, we'll be talking about periodic properties. Thank you.